Welcome to part 4 of the vectors chapter. In this video we're going to look at angles between 3D vectors and the axes, and then just do a couple of problem solving questions. So in the previous video we looked at magnitude direction form of a vector, but that was just in 2D. We used trig to find the angle and Pythagoras to find the magnitude. What we can also do is find the angle between 3D vectors and each of the coordinate axes. The formula is there in the booklet. I'm just going to show where this comes from. So the 3D vector xyz, xi plus yj plus zk, makes an angle theta x, so we use a subscript x to denote that it is with the positive x-axis, theta y is for the y-axis, and theta z obviously for the z-axis. And the way we do it is just that formula there, which is not in the formula booklet. Nothing in this chapter is in the formula book. So that's something, this is a formula you need to learn. So good idea to make a note of it in your formula booklet in the back with all the others that you're going to be learning. So that's the formula for the angle to the x-axis. Similar formulas exist for the angle to the y-axis, angle to the z-axis. Notice they all involve cos. You'll see why in a moment. For the angle to the x-axis, we take the x component, or the I component of the vector, and divide by the magnitude of the vector. Angle to the y-axis, we take the y component and divide by the magnitude. And for the angle to the z-axis, we take the z component, or the k component, and divide by the magnitude. So three very similar formulas. You'll see why using this diagram here. So let's just get rid of all my additions first. So the vector A is drawn there. It's the vector that takes us to the coordinate 2, 2, 8. So the vector itself would be 2, 2, 8, or 2i plus 2j plus 8k. And I want to find the angle that that vector makes with the positive x-axis. So the positive x-axis is down there. So what's been done is a line has been dropped from the vector to the x-axis to create a right angle at that axis. And the angle we want is the one in that right angle triangle. So, since it's a right angle triangle, it's just going to be trigonometry. Since that coordinate is 2, 2, 8, it is 2 along the x-axis, 2 in the direction of the y-axis, and 8 in the direction of the z-axis. Those two I'm going to make dotted because they're not needed. Then they are not part of the right angle triangle I created by dropping the line to the x-axis. The only value there that is attached to the x-axis is the 2, the first 2, the x component. So that 2 there is the adjacent to the angle I'm looking for. I don't know the opposite, that would be here, but I don't know that. But I do know the hypotenuse, or I can find it. I can find the magnitude of the vector. I don't need to find it. It's this, I'm just deriving the formula. So using trigonometry, I know that cos of that angle is adjacent over hypotenuse. The adjacent is the 2. The hypotenuse is the magnitude of the vector. And that 2 came from the x component, or the x part of the coordinate. And that's where the formula comes from. Cos of the angle we want is the component we're interested in, the x in this case, divided by the magnitude. You can see similar things for the other two. Same vector, but the line dropped to the y-axis this time to create the right angle. So the vector was 2 in the x direction, 2 in the y direction, 8 in the z. but the only value there that's useful to us is the 2 that came from the y component. 2, 2, 8, that 2. The angle we want is to the y-axis, cos theta y. Again, it's adjacent over hypotenuse, which is why we're using cos. And it's the 2 over the hypotenuse, which is once again the magnitude, and that 2 was the y component. And then similar for z, same vector. This time a line dropped to the z-axis to create the right angle. The angle is there between the vector and the z-axis. We've got 2 there, 2 there, 8 there. But once again, the only value that's useful to us is the 8. It's again the adjacent and the hypotenuse that we're using, so it's again cos of theta z equals the 8 over the magnitude, and that 8 was the z component. So that's where the 3 formulae come from. You don't need to reproduce that, but you do need to learn the formulas, or if you don't learn them, remember where they came from. So by this point now we've found the directions for vectors in 2D, and we've got a direct way of finding the direction for vectors in 3D as well. So the first example asks us to find those 3 angles, the angles that this vector here makes with the positive coordinate axes, in other words theta x, theta y and theta z. So applying the formula, cos theta x is the x component divided by the magnitude. X or I component is 3. Magnitude, I'll just work out over here. Don't need to worry about the negative. So that's 9, add 25, add 4, so that's the square root of 38. So that can go back over here into my formula, square root of 38. So the angle that we're looking for then is the inverse cos of 3 over root 38, which from the calculator is 60.9 degrees. So 3 significant figures. And then similar for the y and z. Y over mod a, so the y component is the negative 5. Negative must be included. Over root 38. So inverse cos again. And to 3 significant figures, that one gives me 144 degrees. And then finally, the angle to the z-axis, the positive z-axis. I was meant to write mod a there. So the z component of the vector is 2 over root 39. And the calculator gives me 71.1 degrees. 3 significant figures. Okay, it's important to note that these do always find the angle to the positive coordinate x-axis, z-axis, y-axis, always to the positive axis, not to the negative. Final one for this video. Find the angle that this 2D vector makes with the positive y-axis. So, 2 ways I can do this now. I can do it using a quick diagram. So there's my diagram. 5, negative 8, so it's 5 across, 8 down. The angle I want is the purple one. To get there, I could use trig to find the blue angle, and then the purple one is what I want, it's theta y. So I'll start by finding this one, I'll call it phi. Tan phi is opposite over adjacent, 5/8. So phi is the inverse tan of 5/8. 2 to 3 sig fig is 32.0. Subtracting that off 180 gives me 148 degrees. So that's how we did it in the previous video, earlier on in the topic. Looking at the method we just found, we could use the formula. First of all, I'd need to know the magnitude. So mod A, square root of 5 squared plus 8 squared, which is root 89. So then cos theta y is the y component over magnitude of A, which is negative 8 over root 89. And then you can inverse cos that. Inverse cos of negative 8 over root 89 is 148 degrees. So you can see either approach works. It's just important to note, as I've already said, that this method, the 3D method, always finds angles to the positive axes. So by using it here, we went straight to that angle, bypassing that one. But the angle labelled phi could be useful for some other part of the question. So it's important to note which angles you are finding. So a diagram is always useful regardless. Okay, and that's the end of this video.